Hi, today our group will be presenting about a mechanical standing wave. My name is Dan. In physics, mechanical transverse standing wave is a wave whose oscillations are perpendicular to the direction of the wave's advance. A simple example can be given by the wave that is created on the horizontal string, anchored at one end and moving to the other end up and down. A standing wave occurs when an incident wave meets a reflected wave on a string. The points in the standing wave that appears to remain flat and do not move, we call them nodes. The points which reach the maximum oscillation height, we call antinodes. In our first lab, we fixed the frequency and had a mass as a variable to create different number of nodes, and continue finding more variables from that. This time, we had two experiments, each time with different fixed mass, and under each mass, we try to find frequencies that create different number of nodes. And as a result, we came up with some equations and some graphs that talks about more variables like velocity, linear mass, and tension. Thus, the purpose of this activity is to investigate the relationship between the tension, linear mass, and velocity with changing frequencies, and to have statistical knowledge about our calculated result.
So I'll present the materials first. So all we need is the vibrator, string, pulley, stand equipment, different masses, and passcode. So for the procedure, we should attach one end of the string to the vibrator and let the other end of the string go along the pulley, and at the end of the string, you should choose a fixed value of mass and hang it. So based on the equation we learned from class, we should estimate the frequency that will produce nodes varying from 1 to 5. And finally, using passcode, we should check whether our estimation was correct by observing the actual formation of node. So for example, I already set up the mass at 300 gram, and we estimated that one node will be produced when the frequency is 84 Hz. So let's check whether our estimation was correct. As you can see, one node is produced when the frequency is 84 Hz. It supports that our estimation was correct. So moving forward, I will check two more times. For this time, we will check that 3 nodes will be produced when the frequency is 167.8 Hz. So let's check. So as you can see, 3 nodes are formed, one here, and one here. And lastly, so this time, we will show that 2 nodes will be produced when the frequency is 125.7. Let's check. As you can see, 2 nodes are produced, one here and the other here. For the results, when the mass was 300 grams, one node was formed when the frequency was 84 Hz, and 2 nodes were formed when the frequency was 125.7 Hz. 3 nodes were formed when the frequency was 167.8 Hz. 4 nodes were formed when the frequency was 209.7 Hz. Lastly, 5 nodes were formed when the frequency was 252 Hz. When we decreased the mass to 200 grams, one node was formed when the frequency was 70 Hz. 2 nodes were formed when the frequency was 103.7 Hz. 3 nodes were formed when the frequency was 138.4 Hz. 4 nodes were formed when the frequency was 172.5 Hz. And lastly, 5 nodes were formed when the frequency was 209.5 Hz.
Hello everyone, my name is Jae Yong Lee, and so now I'm going to talk about the calculations and conclusions that we have from this our experiment. So for the first equations, these are the equations that shows the relationship between wavelength and the length for every antinode. Also, these are the equations that shows the relationship between frequency and velocity for every wavelength. We use these equations to get the theoretical frequency and compare with our measured frequency. the next equation is this linear equation. This linear equation shows the relationship between frequency and a node, and we extracted this equation from the equations of this wavelengths. The last equations that we used is also another linear equation, and this is the equation that shows the relationship between velocity and the tension, which is mg. And through this linear equations, we are able to calculate the linear density. Now, let's get into the calculations and conclusions that we have from this experiment. Now, let's get into the conclusions and calculation for this experiment. For the calculations, we were able to get the theoretical frequency for the first part and the second part of the lab. Comparing this theoretical frequency to the experimental frequencies, we were able to see a small percent difference for both of the experiment, which was only about 1.2% difference average. Now, and through the data that we measured, we were able to get this graph and see get the slope. Through this slope, we were able to get the velocity and compare with the velocity calculated from our data. The velocity that we got from the graph was 102.48 for the first experiment. And comparing this to the velocity we calculated from the data, it was only 1.2% difference. For the second part of the experiment, the velocity that we got from the slope was 86.27 meter per second, and the velocity that we got from the data was 84 meter per second. Comparing this to, there was only 2.7% difference, which was really small. For this last part of the experiment, we were able to combine all the data of velocity that we got from the first part and the second part of the experiment and make a graph with the calculated tensions. This graph gave me a linear graph, and a slope from this was able to use to calculate the linear density of our combined data. The linear density we calculated was 0.60056 kilograms per meter, and the theoretical linear density was 0.0034. Comparing this to, the percent error was 63.43%, which was a high percent error. In conclusion, we were able to see the relationship between frequency and the number of nodes from this lab, and also we were able to see how different mass affects the overall frequency. So, as the frequency increased, number of nodes also increased as well. Moreover, changing the mass and decreasing the mass also affected by decreasing the frequency. Finally, we were able to calculate a linear mass density from our collected velocity data from our first and second part of the experiment. The calculated linear mass density from our data was 0.0056 kilograms per meter, and our theoretical linear mass density was 0.0034 kilograms per meter. The percent error was high, and we assumed that this high percent error came from our small number of experiments. In the future, we will be doing more experiments to get a more precise and accurate data. Thank you for watching our video.